So my favorite star is the one that's closest to us. It's the sun. My favorite quote from a colleague of mine from Stanford was that the sun is the only star we know of that grows vegetables. The sun is a life-supporting star. You know, it provides energy and heat and light and sustenance to all the life forms on the planet. Even fairly primitive cultures used the sun as a timekeeper, you know, when to harvest, when to sow, all those different things. And we're starting to ask questions today whether other stars can do the same, can support life and help grow vegetables on other planets. One of the things that you're familiar with are the solstices and the equinoxes. We call it the reasons for the seasons, and it's the fact that the Earth's rotation axis is tilted relative to the plane that contains the sun and the Earth. So the Earth, it rotates, but it rotates at an angle. And that means the light shining on the Earth is different at different latitudes. As it goes around the sun, on this side, the northern hemisphere is pointing away from the sun. On this side, it's pointing towards. And that tilt gives us that changing heat input, if you like, and that's the reasons for the seasons. And so the solstices is where the sun is its maximum altitude, north or south. And then the equinoxes is where it's passing across the equator, equal day, equal night. So as we build up those patterns and as we learn those patterns, we start to understand a kind of characteristic model of our solar system and the relationship between the Earth and the Sun. It's important that we look back to see how our Sun went from a mere traveller in our sky to the central anchor of our solar system. For many millennia, the idea was that the Earth was at the centre of the universe and everything that we saw went around the Earth, including the Sun. And it took a lot to shake that. The early cultures, including the Greeks, who were very sophisticated, thought of the heavens as the purview of the gods, right? And so Earth was flawed, people were flawed, but space, the heavens, the planets, everything we saw in the sky was perfect. That was the realm of the gods. And so Aristotle, who many of you have heard of, he was a very obviously famous philosopher, did a lot of measurements of the natural world, essentially dictated that because the sky was the haven of the gods and everything had to be perfect, all motion had to be perfect as well. And so he essentially by diktat stated that anything in the sky had to be considered perfect, and that meant they had to move in perfect circles, which is the perfect shape. So, in other words, every object in the sky had to travel in a circular orbit around the stationary Earth in a perfect uniform motion and keep the same velocity. Aristotle's dictate lasted for almost 2,000 years, 1,600, 1,700 years. However, the problem with this model is that it couldn't explain the strange patterns of the planets, which did not follow a straight line around the Earth. When tracking the position of a planet over several weeks, it appeared to make a zigzag pattern or a small loop against the backdrop of the stars. And it does this little dance, so it's moving across the sky in this direction, and then it goes back, and goes back. It does this little wobble. And so Aristotle's Earth-centered model couldn't quite explain that. So one of the most famous things that had the Earth at the center was the Ptolemaic model. In order for Ptolemy to explain the patterns of the planets, he had to come up with a model, a collection of circles called epicycles. And so the way that he did it was, so the first circle was the planet going around the Earth in a circle. And so what he did was he said, well, there must be another circle on top of that that is causing that little deviation. So he would add a little circle to that big circle. That's known as an epicycle. And so as he did that to try and explain the motion of all the planets that were known then, up in the 6 planets up to Saturn, he added circles and circles to these circles in order to explain the data that he saw. And it all worked fairly well and fairly accurately. He could predict where the planets were going to be in the sky at any given time. Of course, the longer you wait, the tiny errors in that kind of add up. Jump ahead 1600 years and you've got Copernicus. And he hypothesized that the sun was at the center and the earth went around the sun. He was afraid to publish this, and in fact it was a German student who came in to work with him who essentially published his work on his deathbed. And so he came up with this model, and again he was pinned, if you like, by the fact that the motions had to be circular and had to be uniform. And so he, while putting the sun at the center, which we now know is the correct orientation, he still needed circles upon circles, he still needed epicycles to explain the data. And anyway, so that was a Copernican model. We know it to be correct, but it still had this structural complexity that didn't make any physical sense, but mathematically it seemed to work. Then came Galileo, who provided evidence for the sun-centered model using the telescope. When Galileo turned his telescope to the planets, he noticed that Jupiter had some bright objects that were close by. These are now known as the Galilean moons, and he noticed that by watching them consistently, those moons were orbiting Jupiter. So what did that do to the psyche in terms of the Earth-centered universe? If the Earth is the center of the universe and everything goes around the Earth, that means everything goes around the Earth. Galileo saw that there was at least some objects that were not orbiting the Earth, they were orbiting Jupiter, and then the system of Jupiter and these moons was orbiting the Earth. So that allows for a different center, even if it's a local center. Kepler came along and was trying to explain the music of the spheres. He was trying to understand those patterns that he believed was God's work, to understand the motion of all these planets and so on. And he became a firm believer in the sun-centered model of Copernicus. Again, at least initially, he was stuck with circular motion and uniform motion. One of the big challenges was the behavior of Mars. Mars had the most precise tracking data of all the planets, and it revealed irregular retrograde loops that didn't follow circular predictions. This forced Kepler to abandon the ancient circular orbit model. And he came up with his laws, one of which was to throw out the circular motion, and he came up with this notion of an elliptical orbit. Because it's an ellipse, he also had to change the idea of uniform motion. An ellipse has, instead of a single focus in the center as you would for a circle, an ellipse has two focal points, and the sun is at one of them. And so as you go around in the nearer part of the ellipse, you move faster, and as you go around further away, you go slower. In this model, Mars is further away from the sun than the Earth. The closer you are in orbit, the faster you go. So what that means is the Earth goes around the sun in 1 year, and Mars goes around essentially roughly in 2 years or so. So what happens then is that as the Earth is going around, it's going faster, and essentially it's like the inside lane on a running track. It can lap Mars. And so at some point, when you're looking from the Earth to Mars, Mars seems to go backwards. So Kepler's elliptical orbits explain very clearly how Mars appears to loop backwards in irregular patterns when viewed from Earth's perspective as they travel around the sun. The irregular loops can only be explained by elliptical orbits, not circular ones. And so that elliptical orbit explained all of the behavior of the planets, and he was able to predict them a lot more accurately than using all these epicycles and so on. So that's a little bit of history of the sun and how it got its placement in the center of our solar system.